Okie doke. All right. So first of all, we have 4 weeks left of the class. So 4 times 2, 8 sessions. Of course, 4 of it is not going to be full 100 minutes. We have quizzes. So I'm only going to talk about just the portion of 8.1 and 8.2. I want to put that together, okay? I'm just going to call it chapter 8, which is basically, hold on, let me get rid of this. So, finishing chapter 8 today, and then starting on Wednesday, we start chapter 10, which is Laplace. So let me write it down. Today, we'll talk about chapter 8, which is 8.1 and 8.2 together. And in fact, I'll explain what my goal is for today. And starting on Wednesday, we'll start chapter. What is Wednesday? 25th. We start chapter 10. And we should be able to finish that in 2.5 weeks on 5 sessions, including quizzes. And so the last week, I'll just touch on solving differential equation using series or Frobenius series. That's what it's called. Okay. Now my goal today is to explain where this formula is coming from. In fact, this formula is the formula we're going to use to solve for the particular solution of a non-homogeneous linear system. Okay, so let's start with this. Basically our goal is, we have a system x prime equals a x plus f of t, okay, where x is some x of t functions. It's a n by 1 vector here. A is n by n, f of t is n by 1. So we know how to solve this one, right? You find n linearly independent vectors and then this is what we did. So we said the complementary solution of the homogeneous part was c1 x1 of t plus c2 x2 of t, and so on. The last one, cn xn of t. And that's what I did on the exam. That's what I did in the quiz, right? Now, we're looking for the particular solution, in this case, xp of t. So what I'm going to show is that xp of t is this formula right here. So my goal today is how that formula is proved. Okay, proof of that and where it's coming from. Of course, you can see the same f of t, so we sort of have to define and talk about where that piece is coming from. Okay, and it's very similar to the variation of parameters method that we had in chapter 5. All right, so let's start with this. Any questions before we begin? Let me call it 8.1, which is talking about the fundamental matrix. So once again, let's consider this system where this guy is n by 1, n by 1, and this matrix is n by n. Okay? Assume we already have found the n linearly independent vector functions, In fact, we know, x sub I was e raised to lambda I t and then times v sub I, the corresponding eigenvector that you find, right? So we have n of those linear independent, and of course they satisfy this equation. So this is true, and we know since they satisfy this equation, that means xi prime is a times xi, okay, for I from 1 to n. All of these guys, basically, these guys. All right, here comes the definition. So definition is, I want to define this matrix. Actually, let me do it this way. Let me do it this way. Consider an n by n matrix, n by n matrix. It has n columns, right? I'm going to let the first column of this matrix be the vector x1 of t. This guy right here, because this is an n by 1 vector. So I'll place it as the first vector. The second vector is going to be x2 of t, right? And until the last one, which is xn of t, right? This is an n by n matrix because each of these guys, it's a column by n, rows. So we have first column, second, and then the nth column. Each has n entries. That means it's going to make a matrix n by n. I'm going to call this matrix phi. It's a Greek notation, phi of t. Okay. All right. What does this matrix? What's the property of this matrix? So I'm not going to name it now. Let's see what the property of this matrix is. Let's look at it this way. If I multiply A by phi of t, again, in terms of size is n by n, that one is n by n. So it's going to be A, first vector x1, second vector x2, the last one is x sub n. What kind of matrix are we going to get? It's of course going to be n by n, right? So that matrix is in fact is an n by n matrix where the first column is A times x1, A times x2 is the second column, and the last one is A times x sub n. Basically, you multiply A, sort of distribute it on each column, and that's going to be, again, the first column, second column, and the last column, okay? But we already know these guys satisfy that equation. That means first one is going to be x1 prime, x2 prime, and the last one x1 prime, xn prime, sorry. And this is nothing but, the derivative of this guy. I'm going to put a check mark next to it. That's the derivative of that with respect to t, which is nothing but phi prime of t with respect to t. So what does it mean? It means, is at the end of this column? No. So this means phi prime of t equals a phi of t, right? This means this equation true, or in another word, we can say phi of t satisfies our initial linear system. This guy satisfies that equation, right? Okay. All right. Any questions so far? So because of this property, and so because of this property, we call phi of t the fundamental mental matrix. Basically, it's a very important matrix, okay? And sorry for the noise, extra noise from the kitchen. Someone's cooking, and I'm very close to the kitchen. Sorry, guys. Okay. So we have a matrix called fundamental. Let me do an example. This is question 5 on exam 2, right? The question was, find the solution for this differential equation, for this linear system, sorry. 3, 2, x, y, and there was initial conditions given, I remember, but let's not worry about that. So you start by finding eigenvalues, and you figure eigenvalues lambda 2 and lambda 2, they were complex, if you can recall, 2 plus or minus 3i. And then you found the v1 and v2, which was that eigenvector, right? So one of the v was I1, that's 0, 1 plus I 1, 0. And then you do that multiplication, and you eventually end up with these two functions for x1 and x2. So x1 is negative negative e to the 2t sine 3t e to the 2t cosine of 3t. And the work for this is given on the solution that I posted on e to the 2t cosine 3t e to the 2t sine. Okay. Oh, you guys cannot hear background noise? Good. Makes me happy. Seriously? Okay. So it's not bothering. Okay. Now, so we got x2, x1 and x2. So for that reason, the fundamental matrix. So E fundamental matrix is phi of t. Now, can someone tell me what's the size of this matrix? You can type it in the chat. Yep, it is 2 by 2. I mean, you have two vectors, each is 2 by 1, so the matrix is going to be 2 by 2, and that's a very small matrix that I wrote. So it's going to be a 2 by 2 matrix. 2. Why am I starting 2 again? So e to the 2t sine 3t e to the 2t. There's a negative here. Cosine 3t. Basically, making a copy of x1 here. So that's a copy of x1 right there, and then a copy of x2 on the second column. To the 2t cosine 3t. Okay, that's an example of fundamental matrix for this system, for that system. All right, I'm not going to need this. Anybody has questions? Does anybody has question? I need this piece here. All right. Now let's continue. Let's continue with this. How would we write the general solution of this system? We would write x of t equals, c1 x1 of t plus c2 x2 of t, right? This would be the general, and this is the general solution. Now I want to go ahead and write this in a different form. In fact, I can go ahead and write it as, let's see, what's the dimension of this whole thing? It's a 2 by 1, right? Because that's 2 by 1. And you multiply them by a scalar, it's still a 2 by 1. You add them together, it's a 2 by 1. I'm going to go ahead and write it this way. In fact, you can write this in this way. Consider a 2 by 2 matrix where the first column is vector x1 and this is x2, and this is a 2 by 1 matrix where this guy is c1 and c2. If you multiply back, you get the same vector up there, right? But we named the first one fundamental with this symbol, phi of t, and let's go ahead and call this one, maybe a capital C as a vector c, where that's 2 by 2, that's 2 by 1, and of course, the entire dimension is going to be 2 by 1. So that's another notation for the general solution using the fundamental matrix, right? Let me go ahead and call this x sub c. So let's summarize. X sub c of t can be written as the fundamental matrix phi of t times c, where the c vector is basically the vector of constant c1 and c2, 2 by 1. Right? And we can try it for the example we had up there. So x c of t is going to become, what was it, negative e to the 2t sine of 3t e to the 2t cosine of 3t e to the 2t cosine of 3t e to the 2t. I want to stop repeating that t. See. Right? And it's very simple to check this. I mean, if you multiply, you see this is going to be c1. This vector here plus c2. This vector right there, which is our famous c1x1, c2x2. Question so far? So we can use this fundamental matrix to write the general solution as well. Now, we can also use this to find C1 and C2, which is, a solution satisfying initial condition. So let me continue with this. And if an initial condition, let's say x at some constant a, normally we use 0, right? X of a equals, let's say x sub a is given, right? So what do we want? We want our x, then xc, basically we know xc of a, which according to what we had up there, I'm going to use this equation. Phi at a times c, we know it's going to end up x sub a, right? So this is known. This is known. This is unknown. You want to solve for c, right? Let me write that equation one more time. So we have phi evaluated at t equal a. Basically, the meaning of this is when t equals a, evaluate that fundamental matrix. For example, this matrix phi of t up here, where I have my pointer, on, what's the value of that when t equals 0? Simply plug 0. So it's going to be phi of 0. So phi a times c equals x sub a. All right. Now you guys tell me, I want to solve for c. So I have this matrix times c equals x sub a. And I would like to solve for c. How would I solve for c? It's a matrix equation. So how would I get rid of phi of a? You can open your mic, multiply by the inverse of that matrix. Absolutely. But, hold on a second. Question is Does this matrix have inverse? Does phi have inverse? Hopefully. That's a very cheeky answer. But do we know it has it? It has inverse? Let's see. Let's check where phi is coming from. Phi was the matrix, right? That it has all those x1, x2 through xn columns. And all those columns are linearly independent. So we have an n by n matrix where all the columns are independent linearly. That means that matrix is invertible. So let me explain here. Since phi is x1 through xn of n linearly independent vectors, then phi is invertible. So it has inverse. Okay. Now, since it has inverse, you can multiply both sides by inverse. On the left side, you get the identity matrix, and this side you get phi of A inverse times x sub A. Does the orders match? Yes, they do, because this is n by n, that's n by 1, and we get our n by 1 vector of constants, right? And if that happens, well, you can go ahead and substitute it back, because remember, our general solution was nothing but phi of t times c. But we found c, it's this expression right here. So substituted for c, that means your general solution is going to be phi of t. Phi of A. Inverse of that, it's like first you plug A into phi, find the inverse of that. And then multiply by x sub A. And again, orders match because, nope, not 2 by 1, n by 1, n by n, and this is n by n. So as you can see, the final result is en by 1 vector that we want. Okay, we're about to do an example, so don't worry about it. Do you have any questions on this whole thing? So I'm going to go ahead and go to the next page. That's our first page. Came out nicely. Let me draw my line in the middle. That's my new ruler. So let me write it down again. Xc of t was fundamental matrix phi of t times the inverse fundamental matrix at A, evaluated at A, and then times the initial condition given x sub A. Most of the time, this A is 0. So you're going to have, phi inverse at 0, x naught. Okay. As a matter of fact, let's go ahead and find the particular solution satisfying the initial conditions for the one given in the quiz. For the one given in the quiz, let me see what so the x of 0, which was the little x of 0 and then y of 0, and that example was given as 3 and 0. And it doesn't matter, it can be any number. Okay? And phi of t sorry, this is not explained enough. So this is, let me do it this way. Exam 2, question 5. Particular solution. Solution using phi of t, or basically this equation above. Okay. In fact, let me write it down. We know that particular solution we're looking for is 3e to the 2t cosine 3t, 3e to the 2t sine 3t. Okay. Let's go ahead and write down phi of t, which for us, was x1 and x2. It was this matrix. Negative e to the 2t sine 3t, e to the 2t cosine 3t. Have to squeeze another column here. E to the 2t cosine 3t, e to the 2t sine. Okay, it's a 2 by 2 matrix. So for us, A is 0, right? So eventually, definitely A is 0. This A up there. Okay, so we're going to use that formula. So x of t, that particular solution, is phi of t, phi inverse at 0, and then x naught. Or x naught is 3, 0. So let's find that guy first. That means we need to find phi of 0. So let's start this. But phi at 0. Okay? Phi at 0. So we already have phi. We plug 0 in it. Wherever we have sine, we get 0. So we have a 0 here, 0 here. We have 1 here, and we have 1 right there. Now we need to find the inverse of that. And let me write something. I want to erase it, so I don't know if you want to take it out. Phi inverse does not mean 1 over phi inverse. This is not a function. This is not a number. It's a matrix. Inverse of a matrix, it's a matrix again. Okay. I think we talked about finding inverse of a 2 by 2. That's a simple case, right? So it's 1 over determinant. What is the determinant of this? Is 0 times minus 1, which is negative 1. I'll write down the formula for the determinant. And then we swap the elements on the main diagonal. They're both 0, so it stays 0. And then we negate or change the signs of the off diagonal elements. And if you multiply, you see, in this case, it's going to be the same thing, basically, as phi. Because that's a negative number constant. You multiply as a scalar, you get 0, 1, 0 as well. Okay, so this is phi 0. Oops, sorry, phi 0 inverse. Let me write down the inverse formula. If A is A, B, C, D, then A inverse is 1 over determinant, which is AD minus BC multiplied by this. This matrix is called adjoint. It's swap A and D, that's D. And then negate F, the off diagonal. And that's what we did here. Okay, now we found that piece. We already have this. Set that up and multiply. So S of t equals that big matrix right there. You know what? I'm going to do something useful here. You see this 2 by 2 matrix here? That one right there? All the elements have e to the 2t. So let's go ahead and pull that out. Okay? So we e to the 2t. We don't have to write it 4 times. Negative sine 3t cosine 3t. I was about to write e to the 2t cosine 3t sine. Is this required? Room is not locked. Okay. That was phi. Inverse, we found it. All right. What's the last column is x naught, and x naught was 3, 0, if you can recall up there. Good. And you can see, you know, dimensions match. So this is 2 by 2, 2 by 2, 2 by 1. So we're going to do this multiplication first, which gives us a 2 by 1. So e to the 2t. I have to repeat this, unfortunately. Negative sine 3t, sine 3t. All right, what is this multiplication? It's 0, literally 0. And what is this guy? That's 3. Right? And if you multiply that, you get e to the 2t. And you can see. So sine times 0, 0, that's 3. Sine 3t. And then 3. Sine 3. And if you multiply the scalar inside, thus x of t is 3 e to the 2t cosine 3t. 3. And there we have it, right? And that's exactly what we expected. I mean, that's the final answer, question 5 in the quiz, if you look at the solution. And we wrote it up there. And as you can see, it basically skips. It doesn't skip. You're finding those constants anyway. You are finding C1 and C2 because on the quiz, what you did extra upon finding the general solution, you went ahead and find a specific C1 and C2 satisfying the x0, you know, equal 3, 0. Whereas this multiplication right here, it does it automatically, finds it for you, and then you multiply by, you know, this matrix. And you get a final solution. Okay. Any questions? In fact, this was 8.1. So let me write down the problems I'm going to have you guys do on 8.1. On 8.1, I'll post it on e-learning as well. On 8.1, do problems 1 through 8 only. Okay, someone's asking, this is just a better way to find the vectors. I mean, what vectors you're talking about? Because the x1 and x2, you're going to have to find it the same way, right? In the general solution x sub c, you have c1, x1, c2, x2. So these two, they're found, you know, the same way. You're going to have to find eigenvalues and eigenvectors and set up, you know, the whole e to the lambda t times v. This process is the same for both of them. But in the fundamental matrix, you put x1 and x2 as the columns of that matrix. You plug in, you know, the initial value, you find the inverse, and then you do this multiplication to find that particular solution. If you don't want to find a particular solution, you don't even have to do the, you know, the fundamental matrix. You can just go with this because that general solution works well. But yeah, it's a way of finding C1 and C2. Without setting up those linear systems. You know, you get equations of 3C1 plus 5C2 equals 7. And you get another one, you know, 2C1 minus 4C2 equals 5. And then you do elimination, substitution, or whatever to find C1 and C2. Whereas for this one, you don't have to worry about finding C1 and C2 separate. It does it for you. This matrix multiplication, this whole thing does it for you. Anything else? I'm going to go ahead and erase this part. Okay. All right. Now I'm going to continue to 8.2. I think we're going to finish earlier today. And we can, do problems if you want, or just finish early. So this is 8.2. Again, on 8.1, you don't have to do all problems, only just do 1 through 8. And that's a practice of finding fundamental matrix, basically. All right, so 8.2, in fact, that's our goal. Non-homogeneous linear system. Right? So what was a non-homogeneous? Come on, consider x prime. We already studied how to find solution for this part, but non-homogeneous has a non-zero part, a vector added to that, right? So here, f of t is a non-zero vector. It makes it non-homogeneous. Okay. This is what we're going to do. And by the way, in chapter 5, in 5 point, I think it was 5.5, we talked about two methods to find the particular solution satisfying the f of x in that case. And over there we had the equation equal f of x. We had two different methods. What was those methods? And you were questioned on them on the exam, both methods. One was in type, you can open your mic. Yep, one of them was variation of parameters, and the other one was undetermined coefficient. And if you can recall, we said variation of parameters solves the ones that you can do in undetermined coefficients. Basically, it covers a bigger category of equations that you can solve for particular solution part, y of p in that case. So I'm going to save time here. I'm not going to talk about undetermined coefficients, okay? Because what can be done with undetermined coefficients, you can't do it with variation of parameters. But there are cases that you can do with variation of parameters, but undetermined coefficients cannot find those. Easy example, like secant of x. That was the question you guys had on the exam, right? Part C of question 1. You would have to do, I didn't tell you what method you use, but you had to use the variation of parameters where the formula was given in the bottom of it. Or wasn't? Anyway. So what we're going to use here, so we'll only talk about variation of parameters. Only. And just like I explained, you can do the ones that like you would do with undetermined coefficients. It covers all those sort of problems. All right. Continuing with this. So up there we said, let's mention this. We know x of t, the general solution, has two terms. The complementary solution and the particular solution, right? But we showed above that x c of t is phi of t times c, or the other way, it was, c1 x1 plus all the way through cn xn. But from now on 8.2, we're going to continue with this form, where this c was the vectors of c1 all the way through cn, n by 1. All right, so we know this part. Now we're going to focus on that guy. How did we start finding particular solution using variation of parameters in chapter 5? If you can recall, we said, Let me write it on the other side and I erase it. This is just a reminder. So we said, y sub p was in this form, y1 u1 plus y2 u2 plus all the way through yn un, right? And then we were finding u1, u2 all the way through un, right? And it ended up being those integrations in the variational parameters formula. We're going to do the same thing. So here, we, so similar to chapter 5, assume the particular solution has this form. So we would do C1x1, but we're going to do, Cx1 instead of C, we are looking for a function of t. So x1 times u1 of t. In fact, to be precise, this is, x1 of t times u1 of t. Let me write u smaller. So it's a scalar function for now, plus x2 of t, u2 of t, and then xn of t times un of t. So these guys are scalars. So these are scalar functions. But if you write it this way, I'm going to write it in matrix form, right? So put these x1 through xn in a matrix n by n, and then u1 through un in an n by 1 matrix. Basically, it's the same as, C1 through Cn, except you're using functions of t. And now I can go ahead and write this as the symbol we used for that matrix, fundamental matrix, times u, right? So now my x of p has this form. Let me write it down here so that we can assume x of p equals phi of t, u of t is a particular solution satisfying what was the equation? X prime equals ax plus f of t. Okay. And by the way, let me remind you something here. We know this fundamental matrix satisfies the homogeneous part. So if you already know phi prime of t equals a times phi of t, we know this, right? So this we already know. Okay, but let's, take a look at this part of this sentence. It says, this guy satisfies this equation. What does it mean? That means if I plug it in, it holds, right? So that x prime of p or xp prime equals a xp plus f of t. Well, let's plug it in and see what happens. So, but let's go ahead and find the derivative of xp prime. It's the derivative of this matrix multiplication. So it's multiplication and we're taking derivative. Obviously, we're using product rule, right? So it's going to be phi prime of t, u of t plus, phi of t times u prime of t. Again, dimensions match. That's n by n by 1, n by n by 1. It's going to give you an n by 1 vector at the end. Then let's plug it in. So xp prime. So this goes to the right side of this equation, okay? So phi prime, I'm not going to write t. So phi prime u plus phi u prime equals a x itself, which was phi u plus f of t. Remember, we want to solve for u. That's our goal. We want to see what u makes this guy right here a particular solution. All right, I'm going to substitute something. What phi prime is, right? Phi prime satisfies that equation. So we have a phi u plus phi u prime equals the right side a phi u plus f of t. So we have two similar terms on either side. We go ahead and cancel that. So we have phi times u prime equals f of t. Okay, at least you have an equation that has, only u prime in it. Can we solve for u prime? Yes. You have to multiply by the inverse of phi. Invertible? Yes, it does. Because, made the argument that it's an invertible matrix. So u prime, I'm going to use the t variable. U prime of t equals the inverse of phi at t. So this time we haven't not plug in any t in the phi. It's going to be just the pure function of t. Right? It's a function. It's a variable. Inverse times f of t. Good. We're able to solve for u prime. Now, how do you go from u prime to u? U antiderivative. It's going to be antiderivative phi inverse of t times f of t dt. And let me remind you that this is n by n. That was a vector n by 1. And of course, this u prime is an n by 1 vector. So same thing. This is n by 1, n by n, n by. That means right here is going to be a matrix multiplication. We do an examples. So, but, if we can recall, xp of t we said is phi of t times, if there is some u of t, and there is, because we found it, equals phi of t. All right, now replace ut, which is that integration. Integral phi inverse of t times f of t dt. There we have it. That was a formula we were talking about at the beginning. Although I have 1, 2 more pages. Actually, no. Talk about this. Talk about this. I'll talk about this one. Okay. So as you can see, if this is the particular solution, so that the general solution which was, x equals x sub c plus x sub p equals, so x sub c, we figured, it's phi of t times c. That's the vector of constants, c1 through cn, plus, and xp phi of t integral phi inverse of t f of t dt. How beautiful is that, isn't it? That's beautiful, right? They can get a particular solution just by that. All right, questions? We can do a break. It's 4:50. So, we can take a longer break. Because after this, I'm only doing an example. Actually, let me mention this, and then we go for a break. Let's see what this formula becomes if you have an initial condition given. Okay. In fact, you already know about this part. So if, x of a equals x sub a is given. First, you're looking for an x of p where x of p at a is 0. Because here's the reason. Because, remember, that part of the homogeneous linear system solution satisfying x sub a was equal to, if you can recall, was phi of t, right? Phi inverse of a and then x sub a. Now think about it. We have xp of a. So this is the general solution. I want this solution to satisfy this guy right here. I want to repeat again. I want this solution, this whole thing, satisfy this guy right here. Meaning, if I replace t with a, the whole thing becomes, this side becomes x sub a. Let's see what should happen for this, to satisfy basically this requirement. If I plug a here, I get phi of a times phi inverse of a. What is that equal to? And by 1, you mean, remember, these are matrices. So if you multiply matrix, identity matrix, beautiful. This is I. And you multiply XA, which is a vector, so it's going to end up being XA. So this whole thing is going to be X sub A. Now, you want this whole thing to be X sub A. You want this whole thing to be X sub A. If you want this to be X sub A, that means you prefer this guy to be 0. Okay, now, so, and that's very simple. All we have to do, we need to determine what limits we should give to this integration. Pointing out to those. So the limits of this integration should be something that makes this whole thing 0 if you plug A. And that's very simple. I'm going to erase some of these guys. So erase that, erase this, erase that, erase that. Okay. Let me erase that one as well. Well, for this to be 0, let me ask you a calc 1 question. What's the integral of 2 to 2 x cubed plus 3x minus 1 dx? What's that integration? It's 0. It's 0 because, you're going from the same limit to the same thing. In fact, you're considering an area where the bottom, the base, the length of the base is 0. Like you're not even shifting left and right. So it's a rectangle with the length equals 0. So it is 0. Okay. So what we have to do is that we make that integration. So let me write the first piece. That's my first term, which is the, and then behind that integration, why am I doing this? I have room. So plus phi of t. Okay. And then let me write down the integrand. That's phi inverse of t dt. Oh, I want to change the variable of this integration. So let me change it to, so phi inverse of s, f of s, and then we can evaluate it at t, okay? Now, this integration, you do it and then you evaluate it at t, eventually becomes a function of t, where t is a variable. My question is, what should the lower limit be so that if I plug a for t, the whole thing becomes 0? So what should be the lower limit be? And remember, you plug in a for t eventually, and you want that integral to be 0. So when you plug it in, your integration is going to be from something to a, but you want that integral to be 0. So what should be this guy for it to be 0? Beautiful, a. Now that integration, if you plug a for t, no matter what the integrand is, it's 0, right? So for this solution, x of t. So for this particular solution satisfying this initial condition, if you plug a for t, we already argued that that's I, so this whole thing is x sub a. And that integral is 0, because you're going to have an integration from a to a. So you'll be safe, okay? Let me rewrite it in the next column, or next page, actually. Let me zoom up here. On the next page, draw my line. Zoom in 140%. So x of t at the end is phi of t, phi inverse at a, x sub a, Again, that was the x sub c part, plus phi of t integral a to t phi inverse of s, f of s, es, and we integrated from a to t. And this is x sub p part. Good. All right, let's do a break. So let's do a break for, let's do it for, and I mean, 56, so to 05. It's going to be what, 9 minutes? So 9 minute break. 9-minute break. I'll close my mic. I'll see you guys in 9 minutes. Good? Everybody good? No complaint? No questions? We'll be back in right now 8 minutes. Hi guys, I'm back. So let's go ahead and do one example. Okay. So let's do a very simple one. Reduce detail as much as we can. Let's do just number 1, 8.2. 8.2 exercises. On problem number 1. So it says basically apply the method. Here it says undetermined coefficients, where we're going to use variation of parameters. So use variation, use variation of parameters, solve the find general solution to find. Let's just focus on particular solutions. So we'll find the particular solution of the given system. The given system. And as you can see in the formula above, the big part is finding phi of t, right, and then a bunch of multiplication, matrix multiplication, and then doing this integration right here. Okay, so the given system is this guy. So as I said, it's number 1. It's x prime equals 1 plus 2y, not 1 plus x plus 2y plus 3, y prime equals 2x plus y minus, which, can be written in matrix form as x prime, y prime. What are we doing for quiz on Wednesday? Chapter 8, 8.1 and 8.2. 1, 2, 2, 1. Like this stuff we're talking about now. X and Y, like finding a particular solution using variation of parameters, or find just fundamental matrix. Oh, format, camera scanner, same thing. So same thing you guys did for the exam. You do it for the quiz. So post the quiz with 2 or 3 questions. You do the same thing. I'll give you an extra 10 minutes to scan and submit. Okay, 3 minus 2. So as you can see, this is f of t, right? So f of t is the matrix 3 minus 2. And that's our matrix A, which is a 2 by 2. All right, so to find phi of t, we need to find those, 2 linearly independent functions. And for that, we need to find eigenvalues and eigenvectors. So we're going to have to, do the same thing that we did in chapter 7. So we have the matrix. Let's subtract the lambda. It's lambda and then 2, 2, which is 1 minus lambda squared minus 4 equals 0. Let's not FOIL this. We can just bring 4 to the other side. 1 minus lambda square equals 4. Take square root. Minus lambda becomes plus or minus 2. Then lambda becomes 1 plus or minus 2, right? So your lambda 1 is 3. Lambda 2 is minus 1. Question on that? Okay, now let's find eigenvectors for each. Lambda 1 equal 3. Your matrix becomes, so take away 3 from the main diagonal. So basically subtract 3 right there. It's negative 2, 2, 2, minus 2 times x and y set it equals 0, 0. Both give you the same equations as, 2x minus 2y equals 0, or simply x equals y. So one candidate for such a vector is 1, 1, right? As long as x and y are the same, non-zero, 2, 2, 3, 3, it doesn't matter. All right, lambda 2 equal minus 1. The matrix we're going to get is 2, 2, 2, 2, x, y, 0, 0. As you can see, this one tells you x plus y is 0, or x equals minus y. So for that, we can pick v2 to be, 1 minus 1, as long as they have opposite signs, but, same value. 1 minus 1, or negative 1, 1, it doesn't matter. Remember, things adjust themselves if you change these numbers. Okay? All right. So for that reason, x1 is e to the, lambda 1t, of course, v1, I'm writing down details, which is e to the 3t times 1, 1, let's multiply it, so v1 becomes this vector, e to the 3t, e to the 3t. Similarly, x2 is e to the lambda 2t, v2, so that's e to the negative t, and the vector we found is 1 minus 1. v2 in this case is, what am I writing v2? That should be x1. It's x1. Okay, same. x1. That's x2. That's e to the negative t minus e to the negative t. Okay. Now let's put them in one matrix, and we call that fundamental matrix. So v of t is the matrix 2 by 2 with 2 columns next to, which is e to the 3t, e to the negative t, e to the 3t, negative e to the. Okay. All right. Now let's, so what was the setup? You have to find the inverse of this. So let's go ahead and find the inverse of this, right? So phi of t inverse. It was 1 over determinant of this. What's the determinant of that? It's the main diagonal multiplication. And as you can see, it's a minus. Think about it, doing e to the negative t, e to the 3t. Right? And that's e to the 2t. It's negative e to the 2t. And you have another one, negative e to the 2t. Okay? So the denominator is in fact, your determinant of this is simply negative 2e to the 2t. Right? Which is shown up in the denominator. Okay, let's write down the adjoint. Swapping the elements on the main diagonal, negative e to the negative t goes there, e to the 3t, and we only change the signs of the off diagonal ones. Like that, right? Let's simplify a little bit. So 1 over, negative 2e to the 2t, and then we multiply by this matrix. And let's go ahead and put the negative up there. But take care of it. Negative e to the negative t, e to d, negative e to the negative t again, negative e to the 3t, and then e to the 3t. If I'm making an error, guys, it's going to mess up the whole thing, and it's difficult to find a mistake. Double check my arithmetic math and let me know. This is algebra. So I'm going to push this 1 over e to the 2t inside. I'm going to keep the negative half outside, although I'm going to multiply by negative, so get rid of those negatives and make just one of them negative. So it's division, but you subtract it sort of. So we get half. Here we go. We get e to the negative 3t. Let me know if you have questions. I don't complain. E to the negative 3t again. This one is e to the t. This one is negative e to the t. Open your mic and ask questions. You have a... Good. All right, this is our fundamental matrix. The inverse of fundamental matrix, sorry. The inverse of t. Okay. Now, let's plug it into the formula. So x p of t is, x p of t was, according to the formula, it's phi of t. So phi of t we had up there. It's e to the 3t, e to the negative t, e to the 3t, negative e to the negative t, times the inverse. I have a half. I'm going to go put this half outside the integral. In fact, I can put it in front right after equals.
Sorry to interrupt, but on the phi or the inverse of phi of t, where did all the negatives come from when you're solving in the vector? To the right of the inverse.
All right. So from here, you mean from here to here?
Yes.
Okay. If we can recall, for a 2x2 matrix A, B, C, D, right? It was 1 over determinant, which is this piece. We already found it. And the adjoint matrix was swap the elements in the main diagonal, right? And then negate the off diagonals. So these two negatives are coming from the negation of B and C. So these are the same elements, but just negating them, multiplied by a negative sign. And then this negative, yeah, so that's the A and D, swap.
Okay.
So that's, this negative up here is a swapping with this one. And then these two are the negating the off diagonal ones.
And the determinant came from what again?
Just a multiplication of, determinant of a 2x2, isn't it? AD minus BC. So multiply these two and then subtract the multiplication of those two.
Okay.
Good.
Thank you.
Mm-hmm. Anything else, guys? I mean, this is a good, spot. If you have other questions, please ask questions. We have time to talk about it, or I can explain. Okay, so I'm gonna put the inverse here. I pull that half here. So I have e to the negative 3t right there, e to the negative 3t, e to the t, and then negative e to the t. All right, what goes here now, guys?
3 negative 2.
Beautiful. So it was the f of t part, right? And it was the 3 negative 2. Good. And then dt. And this problem has no initial condition given, so for that reason we don't have to worry about putting limits here from a to t and then replacing all the t's here with a different variable s. So we're not doing it over here. Okay. And I have one tricky question. I mean, the answer is very simple. It's gonna make me dumb even asking that, but let me ask you guys. Let me go up here. Look at this piece. That was a terrible arrow. Look at that guy and look at that guy. Aren't they inverses of each other? Like that's phi and that's phi inverse. Can I just multiply them to get I identity? Get rid of them? Can I do that? Absolutely not. Oh, that was a strong, opposition. Why is that? Explain yourself, please. Why I cannot do that? The answer is correct. I can't do that. It's not a constant. You can pull it out of, you cannot pull it out of integral. That's correct. That's it. Remember, this is not a constant term, can be pulled out of integral. So you have to do this operation first. What is this operation? Integration. You're going to have to do the integration. and then multiply the result by phi of t. Good. See, that was a dumb question that I asked. Sorry. I'm waiting for a new pen, guys. In fact, I already bought the device. I'm just waiting for this new pen. Terrible. Terrible. Stay with me, please. Okay. We are there. All right, so let's do this multiplication first, and then we integrate, okay? So for that, you're doing a 2 by 2 times a 2 by 1. You get a 2 by 1 matrix. Let's see what it becomes. Is that okay if I write underneath, or should I go to the next column? Should I go next column? Next. I'm just going to next place, yeah. I think somewhere I erased that line. I forgot what it was. Let's see. I really don't know what it was. So it's e to the negative 3t, right? E to the negative 3t, e to the t, e to the t. And over here we have kind of reciprocal, transpose of that, e to the 3t. Let's cheat. E to the 3t, e to the 3t, and then we have e to the negative t, negative e to the negative t. That was phi. And then phi in part, let's skip that f, e to the negative 3t, e to the negative 3t, e to the t, negative e to the t. Right? And we have 3 minus 2. 3 minus 2. Okay. So xp of t, it's e to the 3t, e to the 3t, e to the negative t, minus negative t. It's integral. It was that 2 by 2 matrix. I'm going to rewrite it again. Was there a negative on that one? Yes. So it's e to the negative 3t, e to the negative 3t. Oh, there's a half. You're right. Sorry. Half. E to the t, negative e to the negative t, e to the negative e to the t. And then was it 3 minus 2? dt. Okay. Okay, now I can erase this. Now let's zoom in 40%. All right, so that multiplication, it's 3e to the negative 3t minus 2e to the negative 3t, which is just 1 e to the 3t, right? You agree? That's just e to the negative 3t, one of them. And here we have the same thing, e to the 3e to the t, and then minus minus plus 2e to the t, which is 5e to the t, right? So that becomes this, right? It's let me write the whole thing. So it's the integral of that. I don't like write math like this. But this multiplication is that. So we have e to the 3t. Damn it. Don't do this. Integral. All right, now we have to integrate e to the negative 3t, 5e to the t. fact, you'll be surprised when you see the answer. Probably you'll be mad, but let's see. So it's going to be half e to the 3t, e to the negative e to the t. This was just a simple example we wanted to end up being constants anyway. All right, let's integrate this. What's the integral of the first one? Remember, you integrate in the factor, so it's going to be component-wise. It's going to get 2 by 1 way. Antiderivative e to the negative 3t is negative 1/3 e to the negative 3t. Agree? And that one is itself, 5e to the t. And we don't have integral sign. That's terrible. Erase. Damn it. So that was that one. Integral of this e to the negative t. Negative e to the negative t. This guy. Okay. So that was the integration of this guy, right? Respect to t. Now we go ahead and multiply 2 by 2 by 2 by 1, which is half. Okay, this is where you're going to be mad. So I'm multiplying this row by this column. As you can see, it's e to the 3t times e to the negative 3t, which is e to the 0, and that's 1. This negative 1/3 plus 5. Because we have the same thing, e to the negative t times e to the t, that's e to the 0, 1. The other one is negative 1/3 minus 5. Yep, final xp is a vector of constants. And it makes sense because, the f of t was a constant function. All right, let's, so that's what? 15/3 minus 1 becomes 14/3 multiplied by half. It's 7/3. That's just some math that you can do yourself. And this one is negative 15/3 minus 1, negative 16 times half is negative 8/3. There you go. That's the x sub p part. And remember, the final solution of this would be, of that system, x sub g general, which was x sub c plus x sub p plus the whole, c1 x1 plus c2 x2, those two vectors we had, plus this vector right here, 7/3 negative 8/3. So if I give you a question on the quiz, of course not going to be this long, right? Only give you, part of it. I might give you already the fundamental matrix and I ask you to do the rest, like find the inverse of that and then do that integration. I'll only ask you find the fundamental matrix. That's it. The whole problem is very long. Let's zoom out, see how much. I mean, this is a very short one, comparing with the other ones. Question, guys? Oh, homework for 8.2. I'm gonna write it down then. Homework for 8.2. Let's go. Let's just do, so homework for 8.2. Let's do 1 through 13, but use variation of parameter. Using variation of parameters. Remember, if they're given, you're going to have to limit that integration from a to t, the inverse of s, f of s. Yes, right? And outside you multiply by phi. That will be it. I'll make a PDF out of these notes, post it on e-learning, post the video. will the quiz be before or after class? I think it's better to be before class. We start with the quiz. I'll release it at 4. You guys submit it. Except it's gonna, take 10 minutes from the class time. What do you prefer? You want to take it at the end or you want to take it at the beginning? Because I'm gonna do new material. It's gonna be Laplace. Before? Before? Anybody before? Anybody is after? Probably nobody's gonna say after. Okay, we'll do it. We'll do it before. And it's fine. I'll make it shorter so you guys can do it in 20-25 minutes and then take 10 minutes to submit. So the whole length of 4 p.m. on Wednesday. So just like the exam, it'll be released on the Dropbox at 4 p.m. You have 20-25 minutes to write down the answers and finish at the 25th minute. There were people who finished at, they used the whole 2 hours, like 1 hour 58 minutes, and they were trying to do scanning in 2 minutes, which is not possible. And there were a few people of that. And we start Laplace on Wednesday. Anything else? Okay. If no other questions, you can call it. Let me go ahead and